Just 1 minute. I'm
ఎందుకు ఎప్పుడు అడిగి చూసుకుంటాడు అదేదో చదువుకోలే
Yes, where were we in our last class? Hemant? Hello.
So
Yes, where
types
were we
of
in our last
charge.
class?
So types of charging a conductors. How to
Types of charging a
photoelectric affected.
conductor. Charging of a body.
Ma.
Now let us move ahead. Yes, is the screen visible now?
Yes, sir, it is visible, sir.
Fine. So photoelectric effect and field emission. Field emission. Did we see this field emission? Hello. Yes.
Yes, sir.
Yes. Did we see this field emission? Field emission is
Amma.
nothing, but it is similar to the
Auntie,
other forms of charging we have seen. What do we do here? We just keep our sample in a strong magnetic field. Sorry, electric field. This strong electric field, it carries away some of the electrons which are at the surface and thereby making the metal positively charged. Okay, so in field emission also the metal becomes positively charged. Next to this, these are all the 7 methods of charging. Next to it is Coulomb's law. Coulomb's law is law of the interaction between the charges. How the two charges interact with each other. Okay. This states that the two charges, whenever they are situated near to each other in proximity, they will exert a force upon each other. That force is called Coulomb's force, and this force will be directly proportional to the product of charges Q1 into Q2 and inversely proportional to the square of distance between them. Inversely proportional to the square of distance between them. This is Coulomb's. That's it. This is the Coulomb's law. F is proportional to Q1, Q2 and F is proportional to R. So when we write the constant of proportionality, we can write F is equals to K Q1 Q2 upon R, where K is the constant of proportionality, whose value is 9 into 10 to the power 9 Newton meter square per Coulomb square. Got it? Anything here to write down? Yes, Eamon?
Sir, copy it, sir.
Fine. Here K is the proportionality constant, whose value we know already. Experimentally, it was seen that K is equals to 1 upon 4 pi epsilon naught. K is equal to what? 1 upon 4 pi epsilon. Can you tell me what is this epsilon naught here? Yes, what is
It's
this
a
epsilon naught here?
constant.
Can you tell me this?
It's a constant we can say.
Yes, what kind of constant is it? What is its name? What do you call it? This constant of proportionality.
Okay, sir.
Yes, what is it? This
It's a
constant of
constant.
proportionality. It has a proper name. It is permittivity of free space. Permittivity of free space. Now, what is this permittivity? What do you mean by this permittivity? Permittivity 1 upon 4 pi epsilon naught. 4 is constant, pi is constant. What is this epsilon naught? Epsilon naught is permittivity of free space. And what is this permittivity now? Let us see that. This permittivity is the measure of material's ability to resist an electric field. It means we can say how much permission the material is giving. How much permission the material is giving to the electric field to exist inside its own body. Got it? This is the permittivity of free space. Experimentally, it is found out that this epsilon naught is equals to 8.85 into 10 to the power minus 12. 8.85 into 10 to the power minus 12 coulomb square per Newton meter square.
Free space means air, we can say so.
No, 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 not air. Free space means total vacuum.
Only
Free
vacuum.
space, yes, total vacuum outside the Earth's atmosphere. But whenever air is present, for air also we take same epsilon naught, unless it is given, unless it is mentioned. For air also we take same value of epsilon naught. Means same permittivity we take, same as that of vacuum. Okay. If any other medium is present other than the permittivity, then what will happen? Then its permittivity will be written as simply epsilon or epsilon m. Epsilon m. This is also called absolute permittivity. Absolute permittivity of the medium. Write it down. Tell me
So
when it's
copy.
done. Copy. Now next is, see this permittivity 8.845 into 10 to the power minus 12. For each and every material, remembering this permittivity and solving it is little bit difficult task. So what do? We derive a term called relative permittivity. Very important. Relative permittivity. What is relative permittivity now? Relative permittivity is the ratio of absolute permittivity of a medium to the permittivity of free space. ER is equals to E upon epsilon naught or EM upon epsilon naught. Epsilon M upon epsilon naught. Got it?
Yes, sir,
Taken down?
got it.
Yes, taken down.
Even to calculate this relative permittivity, we need to know the permittivity of that medium, no,
Yes,
sir.
sorry, your voice is not clear. What did you say?
Sir, even to calculate the relative permittivity, we should know the permittivity of that medium, no, sir.
Yes, but thing is, permittivity of the medium is calculated experimentally. It can be calculated. We calculate it experimentally. We can calculate that. Okay, but with some sophisticated setups and controlled environment. But to remember them, it's a little bit difficult thing to mention them everywhere. So what we do, we just remember one thing, that is permittivity of free space, and all other things we give it as a ratio, as a multiple of epsilon naught. That's it. Okay, means epsilon naught into epsilon r will give us the epsilon permittivity of the medium. Got it now?
Yes, sir, got it, sir.
Taken down? Shall I move
Sir,
ahead?
copy it, sir. Copy it, sir.
Fine, fine, fine. Now, this permittivity is also known as dielectric constant. Dielectric constant or specific inductive capacity of the material. Dielectric constant or specific inductive capacity of the material. This is a unitless quantity. It has no unit. It is just a number. Always remember this thing. It is just a number. dielectric constant or relative permittivity I am talking about. For metals, relative permittivity is infinite. Relative permittivity for metals is infinite, but for air it is taken as approximately equal to 1. For air it is approximately equal to 1, but for metals it is infinite. Got it?
Yes, sir, got it.
Take it down now. Just now done.
Sir, got it, sir.
Now, this epsilon r or relative permittivity can also be written as force in space divided by force in medium. So we just calculate the force in space and divide it by the force experienced by the charges in the medium. Thus we get epsilon m upon epsilon naught. So epsilon m upon epsilon naught is equals to f naught upon fm. Got it now? Hello?
Sir, got it, sir.
Fine. Next is Coulomb's law in vector form. Coulomb's law in vector form. So do you remember something here?
So, I mean, just we are adding it in a vector form.
See, in Coulomb's law in vector form, what is happening? Uh, 2 point charges are given to us, but those 2 point charges are having a vector position. Means what? Means for both of these two charges, we will be given with the position vectors. Got it? Now, when position vectors are given to us, we do not need the position vectors here. We need the distance between the two charges. And we know that whenever we subtract position vector of one from the second, we will get the relative displacement between these two positions. Got it? So that relative displacement we want now. That relative displacement we want now. So we are writing it here. R equals to R2 minus R1. This is our relative displacement. Got it? Now what will be the Coulomb's law in vector form? If any medium is present, first of all, if any medium is present, then what will be the Coulomb's law? Coulomb's law is 1 upon 4 pi epsilon naught kq upon r square. But if instead of epsilon naught, any other medium is present, then what we will write? We will write epsilon m. And right now we saw epsilon m is equals to epsilon naught into epsilon r. So we can write it like that also, epsilon naught into epsilon r. This will also give us the force in an electric field. Got it now? Similarly here, we are writing force is equals to 1 by 4 pi epsilon naught into epsilon r into q1 q2 upon r square, where epsilon naught is the permittivity of free space and epsilon r is relative permittivity of the medium. And both of them when multiplied, they will give us absolute permittivity of the medium. What is r cap? R cap is direction along r vector, will be given by r vector divided by magnitude of r vector. Therefore now the force will be 1 upon 4 pi epsilon naught epsilon r q1 q2 upon r vector whole square, multiply by r cap. This is r cap actually. This is r cap. See here, this is r cap. And this r cap we are writing r vector upon magnitude of r vector. It will become cube. This is the Coulomb's law in vector form. Coulomb's law in vector form. Got it?
Sir, got it.
Tell me when taken down.
Sir, copy it, sir.
Copy. Fine. Now, next important point is, whenever a medium other than the vacuum or air is present between the two charges, then what will happen? Then we will use epsilon r. Epsilon r instead of only epsilon. Epsilon r into epsilon naught will be used. Okay. Same which we saw earlier. But this epsilon naught epsilon r, we are doing what? We are taking it, we are keeping it same as earlier. And we are taking this epsilon r with r square. So we can write r into under root of epsilon r. What does it mean? It means that now the effective distance between the two charges is increased by root epsilon r times. Increased by root epsilon r times. See, this is written. It implies that the effective distance between charges increased by a factor of under root epsilon r. It means the new distance of this epsilon r under root into r is equivalent to the placing of the charges in the medium of dielectric constant epsilon r. Means if we place the two charges, system of two charges inside a medium, and then we take it out again and increase the distance between the two charges by under root of epsilon r, then we will get same force as earlier. Got it now?
Yes, sir,
Yes,
got it,
Hemant?
sir. Yes, sir, got it, sir.
Fine. Take it down and then solve this question. Find the force if a slab of dielectric constant K is inserted as shown.
So slab means a rectangle for rectangle block.
Not rectangle, cuboid it is. Yes, done. Hello. Yes, Hemant. Am I audible?
So you're audible, sir. Sir,
The question is done. What is the answer?
find the force if a slab of dielectric constant K is inserted as shown. Sir means here we should consider the width also. I'm getting confused.
See, width is given as T. Width is given as T here. And dielectric constant is K. Okay. We have kept the slab of thickness T. Therefore, what will happen? Therefore, we can write 1 upon 4 pi epsilon naught q1 q2 by r square. Now this r is increased by root 2 times. But which r is increased by root 2 times? Only the distance, only this distance which is in between the two ends of the slab. It means if t it was, then now it will be under root t into under root of epsilon r. Okay, now it will be this. But what about the rest of the medium? Rest of the medium will be as it is it not? So total distance, first we wrote it as r minus t plus t, r minus t plus t whole square. And now then, now we can write like this. Now we can write like this because t is equals to nothing but under root kT. Why under root kT? Because K was the dielectric. And what did we see? We just saw that dielectric, under root of dielectric is multiplied by the distance. So under root of dielectric is under root K multiplied by the T distance. Multiplied by T distance. Got the question now? This was easy question. Got it?
So much that thickness also we should consider in the formula. So that,
Yes, what?
so, sir, can you explain this again so I get in calculations?
Which one was the formula or this question?
So this question, sir. Sir, this question can explain, sir.
Yes. See now, just
Yes, sir.
now we studied that whenever a slab is inserted between the two charges, its effective distance increases. If two charges are these and I am inserting a slab, then the force between them will become 1 upon 4 pi epsilon naught epsilon r q1 q2 by r square. This we wrote like this, then it will be k q1 q2 upon epsilon r under root into r whole square. This we can write. Okay. Now here instead of r, here see here carefully, totally between these two charges, full material is filled out. That's why we can write this formula. But if half of the material is filled, then only for half we can write this formula, and half we can write normal formula. Got it? So here it is
Yes, sir.
only for t. Remaining distance is what? Remaining distance will be r minus t. This one and this one will be r minus t. R minus t plus t. So total distance is r minus t plus t. Got it? Got it or not?
Yes, sir, got it. So R
Hello?
minus 3. Sir, got it,
Yes.
sir.
Now we will find the force. What is force? 1 upon 4 pi epsilon naught q1 q2 upon r square upon r square. What is r here? R is r minus t plus t. This is r. Its whole square. Now in place of t, instead of t, slab is there. So what we will write? Under root of k times t. That's it. Instead of t, write down under root of k times t. Got it now?
So, I mean, instead of doing separately, we are doing in a combined two cases in one case only, no, sir.
Yes. Okay. Got it now?
Sir, got it, sir.
Fine. Now next question. Given two charges q1 and q2. q1 is at 2 comma 3 and q2 is at 6 comma 6. Find the force F21. Find the force F21. Yes, trying the question.
Sir, trying, sir.
Done. Yes, done.
So just 10 seconds, 1 minute.
Fine.
Given two charges, Q1 and Q2. Q1 is at 2 count. So we can say it's K Q1 Q2 by also 5 we can
See
write
here,
also then.
what the question is asking.
Okay, sir.
What the
In
question
vector
is
form.
asking. Question is asking. Find the force F2. Means what is the force applied by 2 on 1? Okay. We know that what is the force? Force is K Q1 Q2 upon R square. In vector form we wrote it. K Q1 Q2 we took common and we will multiply all of these. So what do we get? We will get upper limit minus lower limit. Upper limit is yes. Yes
Yes,
now.
sir.
Upper limit is here is what? 6. 6
6,
minus
yes,
lower limit is 2. Similarly, here next upper limit for y is 6. Lower limit is 3. So 6 minus 2 and 6 minus 3. Thus we are getting k q1 q2 upon 125 into 4 I cap plus 3 j cap. Got it now?
yes, sir, got it.
Fine. Solve this question. Next question. A charge q is divided into two parts such that when these two parts are kept at some separation, the force between them is maximum. Find the charge on each point. It's done. Are you doing it?
So 1 minute, so I'm doing.
Fine, fine, try it out.
A charge Q is divided into two parts such that when this Q by 2 and Q by 2 if we divide. Sir, if we divide into Q by 2 and Q by 2, the force will be maximum now.
See, first of all, calculate the total force.
Yes, sir. And we should differentiate with respect to distance.
Yes, yes, yes. When we will differentiate it with respect to distance, then what will happen? dF by dx should be equal to 0. So dF is kq upon r square ka whole square. Okay. And distance is what? Distance is x minus kx square upon r square. Got it? This should be equal to 0. Getting it? While equating, we get q is equals to 2q. A small q of the c, sorry, kq, k and k will cancel out, r square and r square will cancel out. What is remaining here? Q equals to 2x is remaining here. It means x is equals to q by 2. What was the x now? X was the charge, maximum value of the charge on these two parts. Maximum value of the charge on these two parts. Got it now?
Sir, got it, sir.
Now, solve this question. Distance between two charges q1 and q2 is small d in vacuum. When this arrangement is put in liquid, the force between the charges become one-fourth as that in vacuum. Find the dielectric constant of the liquid. Can you do it?
Yes, sir, I can do, sir.
Fine. Try solving it now.
So the question is not visible, sir.
No, this much is the question. That's it. Is it visible now?
Sir, yes, it's so. So now I can see, sir.
What is the answer?
Sir, I'm solving, sir. One.
Okay, okay, fine. Got it now? Hemant?
1 minute, sir. Last calc doing. Distance between two charges Q1, Q2 in vacuum. Distance between two charges Q1 and Q2 is in vacuum.
Yes, got it now? Hello?
Distance between two charges Q1 and Q2 is in vacuum.
Am
When
I
this
audible? Hello?
so you're audible, sir.
Fine. So did you solve this? What happened? See, we need not to do anything here. Just we know that the force becomes half. Ratio of the force is nothing but inverse of the ratio of epsilon. Epsilon was what? Relative permittivity and absolute permittivity of free vacuum, or absolute permittivity of free space. So F upon F by 4 is equals to 1 upon 4 pi epsilon Q1 Q2 upon D square. This one. And similarly, F upon 4 will equal to 1 upon 4 pi epsilon M Q1 Q2 by D square. This will cancel out. 4 pi cancel out. F cancel out. 1 upon 1 by 4 equals to 1 upon epsilon naught into epsilon 1 upon epsilon M. So thus epsilon M upon epsilon naught will be equal to 4. Got this? See, now there are several questions. We need to try them out. And till now, half an hour we have taken. Yes, Hemant, am I audible?
You're audible, sir.
Fine, fine. So, yeah, Hemant, because of one problem, I need to go now. Our half an hour is remaining of today's class. I will send you a file which will be containing several questions of this chapter, electrostatics. Okay, try solving those questions, and I'll meet you next class now. That is from 7:30. Okay.
Yes, sir. Okay, sir.
Fine, fine. Okay. Thank you.
Sir, thank you.
You got the questions? Got the questions?
Yes, sir. I got, sir.
Fine, fine.